Metro System is currently doing a lot of experimenting with AI and machine learning. Some of the issues that AI is trying to solve is infrastructure monitoring, chatbots for issues reporting, and of course, image recognitions of products and of cargo. Now, before we get into the coding, we need to take a small detour and see why this Robonaut platform, it is an old platform, it's 19 years old. Let's see why this is relevant for us. Raise your hand if you can recognize the object in this image. So, this is a small toy. It's called a tortoise. They were produced in the 40s in England. What it can do is move in a straight line, and when it collides with something, it will change directions. Okay. Also, they had a light sensor on the top. It was a primitive light sensor. When it detected a source of light, it tried to move towards it. Now, back then, they got quite a bit of reputation. The press was writing articles about them, and they became famous. Why do you think this object is covered in glass? It's a toy, children will play with it. It's also meant to collide with furniture, so isn't it a bit strange that it's covered in glass? I believe that their author was very proud of them. After they got famous and more known, he started making quite a lot of them. And he was giving them as gifts to his friends, to important people. Starting as a toy, it became an object that would inspire. A friend of William Gray Walter was Alan Turing. In 1950, he came up with something called the Turing test. He claimed afterwards, several times, that it was these toys that inspired him to think about the future of machines, how advanced will a machine one day become. Raise your hand if you can recognize the person in the image. His name is Marvin Minsky. He was working for MIT when in 1951 he built the first randomly wired neural network machine. So he was a pioneer of AI and machine learning. And let's take a closer look at this image. We see him and a video camera, a robotic alarm. The video camera takes images of some white cubes on a black background, and the robotic arm can pick up the cubes and arrange them in a stack. Also, if we take a closer look at the image, we see something a bit interesting. Notice there are some wires on the floor. The floor is not quite clean. The podium looks a bit improvised. And you have this metallic robotic arm. He moves objects around. But every time he finishes an experiment, a person needs to get close to it and scramble the cubes back again. This doesn't look quite safe and doesn't look very pretty. I wonder why they didn't arrange things up, at least for when this image was taken. It could be that they didn't care much about safety, but it's unlikely. A more probable explanation was that they were working with this setup every day for years. They were very proud of them. They had high hopes, they wanted to make some breakthroughs, and they had positive feelings about it. The thought that this could be dangerous, this could be a safety hazard, I don't think it crossed their minds too often. Also note that in this image, what is this image about? It's about a person and about a metallic arm? Not really. It is about a robotic arm that can arrange cubes. The center of attention is the fact that it knows how to stack the cubes, and it can recognize them. This was in the early 70s. Raise your hand, last image. Who can recognize the object? So, this is Shaky. It is a robot developed by Stanford Research Institute. What it can do is recognize objects, recognize, I would say, primitive shapes, and it can move around through a maze without colliding with objects. It has a video camera, and on top of it, it has a rangefinder. What we don't see, because the robot is quite tall, it's tall as maybe taller than a person, it also has a radio antenna. Now, take a closer look at this object and raise your hand if you have heard about the A-star algorithm? A-star algorithm, Hawk transform, visibility graph. All these ideas were either conceived for this robot or was greatly improved for it. What they were trying to do is to create an autonomous robot that can plan its own movements. They would put this shaky robot in a room with such objects. They will let it compute his own trajectory, have a start position and an end position. And he would look around, make computations, sometimes half an hour or so. It was back then. And then he would move and, fortunately, if he was lucky, do not collide with anything. This object is the grandparent of the self-driving car. This is what they were trying to do. Again, look at the image. Look at the furniture. It looks pretty well made, artistically. I'm pretty sure they could have gotten away if they were to make the objects out of cardboard or paper, but they put in a bit of extra effort and they produce high quality, good resolution objects. Could be that the primitive image recognition algorithm really needed good resolutions, but if you take a look at the image again, what does it try to convey? Is it an image about a robot? Sure. It's also an image about a robot that can recognize shapes, that can move through objects. The center of attention is not really the object, it's what it can do. Now, we saw three images, they have something in common. Once they built the object, the focus changed, they were wondering what it can do. They were trying to push it forward. Robonaut is a platform where you do battle with small robotic-like tanks. It has a similar past. It started as a Java tutorial. So 19 years ago, this thing was meant to be a Java tutorial that would teach young people basic Java syntax in a fun, interactive way by programming robots that fight against each other. And what exactly it was teaching? Basic Java language syntax? Okay. Also, what was cool back then? Event-oriented architecture. So listeners, events, stuff like that. Once they launched it as a hobby, okay, it quickly got famous. Universities, researchers, they took a liking to it. And they kind of adopted it. They started to try and test AI and machine learning algorithms. And it also became quite competitive. There is a worldwide leaderboard. Everyone can write such a code for such a robot and submit it there and see how it fares against the best in the world. But bear in mind, it is very competitive. This is a turn-based game. Every turn, the platform asks all the robots, what is your move? It collects all the moves and then starts simulating them. If in front of my radar there is an enemy robot, in that same turn, the platform gives me information about it and asks me again, what is your move? I can make a decision again. Thus, it is very beneficial to scan enemy robots as often as I can, as many of them as I can. The tank has three parts, the body, the gun, and the radar. They can rotate independently, so the gun and the radar can rotate in opposite directions, regardless of the movement of the body of the tank. And each turn, I have to make a decision. A decision is anything from any subset of the following. Move forward, move backwards, turn left, turn right, shoot, accelerate, decelerate, and of course turn the gun and turn the radar. Good. Now let's get a closer look at the game mechanics. Every turn the platform gives me information about my robot. The XY coordinate system has its origin in the lower left corner. And the orientation of my body, my gun, my radar is given to me relative to the OY axis as an angle. It is in the clockwise direction. More rules. Every turn I can accelerate by 1 pixel per turn. Every time I collide into something, I get a little bit of damage. Every time I shoot, my gun heats up. I cannot fire again until the heat of my gun reaches 0. This is to prevent continuous shooting. And of course, every turn, my gun loses a little bit of heat, so that about every 11 turns, I'm able to fire again. When I fire, I need to tell the platform what is my firepower. This is a number between 1 and 3. Bullets with low firepower travel faster, but do less damage. Every time I shoot, I need to pay a cost of energy points equal to the firepower that I choose. Now, this is the formula for bullet velocity. Every time a bullet hits an enemy, I get back 3 times the energy I paid to fire that bullet. And when an enemy gets hit, he loses energy points equal to this formula, 4 times firepower plus 2 times power minus 1. Okay, I start with 100 energy points. My gun can turn 20 degrees per turn at constant speed. My radar 45 degrees per turn. And whenever I scan an enemy, I can see his body orientation, but the platform will not tell me the orientation of his gun or his radar. I can only assume those. It will not tell me. Now, let's talk about how we can score points. It is a competitive game. At the end of each round, the bot with the highest score wins. So, I get 1 point for each point of damage that I cause. If my bullet is the last one to kill an enemy, to hit an enemy and it dies, I get 20% bonus points of the total damage that I dealt with. Whenever an enemy dies before me, I get 50 bonus points. This makes it quite profitable for me, for example, to stay in a corner, let everybody else battle it in the middle, and get 50% bonus points for everyone that dies before me. When I collide with an enemy, we both get a bit of damage. I also get some bonus points. Let's now think about how would a winning strategy look like for this game. So, 19 years old is a lot of time. A lot of strategies have been tested and developed to produce competitive bots. If we look at the global leaderboard, we notice something interesting. The top 20% of the winning bots, they all have something in common. Basically, they all implement the same general idea. And this idea is the following. Every time I see an enemy, every time I scan it, I get information about him. His XY coordinates, his energy, his speed, his distance from me, from other enemies, his distance to the nearest wall, and so on. All this information, these numbers, I can store them. The next time I see that same enemy, I get the same information. Let's call this list of numbers the enemy state. If I store an enemy state now and I see him again, he will have a different state. What does this mean? He took a decision, he decided to move or shoot or turn or whatever, so that from his previous state he ended up in the current state. This is what I want to store. State and the decision that he took. If I'm able to collect information about my enemy, in this state he does this, in this state he does this, and so on. If I get enough information, I can predict his next move. What does predict mean? If I can assume where he's going to move, I shoot at a location. If I can assume where he will shoot, I myself move out of the way so that his bullet does not hit me. Why is this efficient? Why does this idea give me a large advantage? It's quite simple. If an enemy is too random, he's easy to defeat, very easy. I can't prove this rigorously, but suffice it to say, if you look at the leaderboards, random bots don't make it very far, don't make it in the first half. Good bots will be reactive to the current game state. They have some information about their state and their enemies, and they take decisions based on that. Taking decisions based on that means they are predictable. If I assume that what they did in the past they will do again, I'm going to be right most of the times. And the game mechanics. They limit the next position of my enemy. So if he's moving forward now, the next turn he can't be moving backwards, he first needs to disable. If he's turning left, the next time he can't be turning right, he first needs to stop turning. I don't have to predict accurately where he's going to be, I just have to be close enough. So, I want to predict enemy moves. For example, let's say, every time I see an enemy, I store his XY location, I do the end what decision he takes. I do that sufficient. I have a lot of data about him. I can predict in the future, based on his future location, oh, he will do this the same as he did in the past. How practical is to predict the opponent move? Well, in order to come up with a practical way to do this, we must first understand the game limitations. This game has two limitations. With the default configuration, you can see, there are some memory and some CPU limitations. So the platform plus the robots that are battling it out cannot use more than half of the byte of heap space. I cannot store that much data in my robot's memory. And by default, every second there are 20 turns. In a practical way, this means that I have about 40 milliseconds to come up with my decision with my move. Otherwise, I forfeit my move, my robot freezes, the platform considers that I did not choose to do anything. Clearly, we need some efficient data structures. I want to store the X, Y coordinates of my enemies and their decisions, and based on that, predict what they're going to do in the future. One such way is the following data structure. Raise your hand if you can recognize. Okay, so this is a KD tree. A lot of you recognize it. At least it's the graphical representation of a KD tree. This is a data structure that can store information. Every data point is a pair of two numbers. This is a two-dimensional KD tree. As the name says, it is a tree-based data structure. What it can do for us? It offers fast search, fast insertion, and fast k-nearest neighbor. Raise your hand if you know what the k-nearest neighbor problem is. So in a practical way, I have stored data, the XY coordinates of my enemy. I have this data stored in a data structure, let's say the KD tree. Now I see the same enemy again with his current XY coordinates. I want to find out in the data that I have stored which is the entry that is most closer, most similar to his current position. By similar, all these are numbers. I'm going to be using Euclidean distance, so similarity is closeness. And how does the KD tree data structure help us? I'm not going to get into the details, but I'll just say very quick the general idea. So the KD tree is a generalization to multiple dimensions of the binary search tree. In this KD tree, I want to insert a new data point. Its coordinates are, for example, 8, 8. What I do, I look at my 8, 8. I look at its first dimension, 8. 8 is larger than 7. I will be inserting in the right subtree. Then I look at the second dimension, 8. I compare it with this 6. 8 is larger. I will be inserting it in the right subtree as well. This is for insertion. How does it offer k-nearest neighbors in an efficient way? So I have a point 8, 8. I want to look inside my tree, what is the entry most closest to my data point? And we can notice that a data point is a pair of two numbers. We can draw them in a plane. Everything in the left subtree will belong to this blue rectangle. Everything in the right subtree will belong inside the gray rectangle. My 8, 8 point is in the gray rectangle. What I can do is find the most similar entry from the gray rectangle. Okay, I find it. Then compute the distance from my 8, 8 point to the blue one. If the most similar from the gray is closer to my data point than the blue rectangle, there's no need to search inside the blue one. I cut my search space in half. I reduce my search space. This is the idea by which it does a fast k-nearest neighbor search. Okay. Now, if you have downloaded these two links, in the Git repository, you will find an Eclipse project with 3 robots. Don't open it right now. These 3 robots do the following. The third one is very simplistic. It sees an enemy, it shoots at the location that the enemy is at. The first two have identical source code. They store data about the enemy. They store the XY locations and decisions in such a KD tree data structure. When they want to shoot, they predict what the future enemy position will be, and they shoot at that position. Now, I'll show you how to run it. So, we have this Eclipse project. First bot, second bot, third bot. First and second have identical source code. All three bots use the same movement. They move the same. The first one also has a nice readme file with some useful links. And some hints given as comments. Now, let's look at the first bot. In the run method, in this while loop, we decide its movement. Same movement as the other two. It's not really interesting. The magic happens in the on-scan robot. So whenever I scan an enemy, I get to make some decisions. I compute the current enemy state on line 13, and I store it. I store it where? I have such a KD tree for every enemy in the game. After I store the enemy state, I predict where he's going to move. I compute the distance from me to that robot. This is how much it will take for a bullet to reach him, and I predict where will he be after that period of time.
Can you zoom in a bit?
Oh, good point.
Very perfect.
Okay. On line 40, I have predicted his future move. I shoot there. You will get time to read it. Let's see how we run it. So, I start the RoboCode platform. The first thing I want to do is look at options, preferences, development options. I want to make sure that here is a link to where the class files from my robots will be. So, this is the bin folder, this is an Eclipse project. I want to start a new battle. And I say in this battle, I want the first robot to fight against the second and the third. If I click next, I can set here, I want them to fight for 100 games. And I start. We can see them battling it out here. They shoot, they move. All three move in this similar manner. I will increase the speed. And they will fight 100 battles, so we have to wait about half a minute. Now I can see the score. Now, what we can see is that the first bot and the second bot, they have a large advantage over the third one. They defeat the third one by far. They are pretty equal. They have the same source code. There's a lot of randomness in the game. One kind of gets a bit higher score than the other. But the main point is that they have a large advantage over the third. Now, your job now, or I should say our job now, is to take the first bot, improve it, so that it also defeats the second one. So improve the first bot so that it not only wins against the third, but also against the second. And how can we do that? We need to refine it. We need to look at its code, understand it, then change a little bit so that it is more efficient. Here are some ideas on how to refine them. They are also given in the code as hints. I will come by to each one of you and help you set up the thing and answer your questions. Warning, some of these ideas are easy to implement, some of them are hard to implement. Due to time limitation, just do one or two of them. Also, they are just suggestions. It doesn't mean that if you implement them, you're not forced to implement them, or it's just a hint. Okay, so I will move back to the slide with the links. Let's start downloading, installing, and coding.
Didn't show any results, but then I tried the snippet that locks the radar on the enemy, and that kind of pushed it to the wall.
This is adjust opponent count. So by default, the radar spins. Okay, very good. If you have only one opponent, just stick with it. Just move a little bit. You know, the radar is a cone, moves around, inefficient. points kind of regularly. And did you get a higher score?
I mean, all battles were first place, but not by much, like 20%.
It gives you an advantage, but it's more.
Yeah.
In reality, what we see as more complex logic, it could be that when we implement it, it doesn't do that much better, but it is more complicated for us. I'm pretty sure it gave you an advantage, but it's a small one. That's good. Okay. Anybody else wants to say a few words on what it is? Sure.
So I focused on multiple walls, and I figured out it's really complicated to solve it in this amount of time. So I just reduced the amount of the length in which my bot goes forward, thus minimizing the chance that it will hit the wall.
Did it get a higher score? How much do you feel like it gave logic
About
advantage?
100. Just yes, I think
That's very efficient. Okay, so since our time is up, I want to thank all of you for being here, for listening to me, for trying. And I want you to congratulate you because in an hour and a half you kind of found out for the first time about this idea. You kind of understand the mechanics, set up the game. It takes some effort. And you try to improve it, you try to improve the logic. You're all winners. Yeah. Should feel proud. Okay.